Hi, everyone. So we are going to start. For those of you who missed the previous session, I am Sol Carretero. I'm an associate professor in Madrid, and I'm going to chair this session. We are going to start with the poster highlights. So, and all of you that are presenting the posters, you have up to 5 minutes if you want to present your slides, and then the discussion will be after the whole session before dinner at 5:30. We can all discuss the posters there. So the questions are for afterwards. Okay. So we start with Constantino.
Yes. Hello, everybody. My name is Konstantinos from the Technical University of Denmark. Thank you all for coming, and also thank you to the organizers for giving me the opportunity to present this work that I'm actually very excited about. I would like to share with you my PhD project, which is a device that we have called the Casimir latching. Now, I don't give a lot of information here because I want you to come to the poster, but what I can tell you is that this is a nano device that uses the lateral Casimir force to reach multiple stable equilibrium. And our vision, it's still a vision because I haven't been able to fabricate it with all the right parameters, but soon, hopefully, you will be able to attach this device in a series of nano electromechanical systems. And this will enable them to reach stable equilibrium. For example, here on the right, I have drawn two waveguides. The first one up there, you can imagine light going through it. And there is another waveguide on the bottom attached on an actuator. And what this actuator does is that it can push one waveguide next to the other, and it can take the light, evanescent coupling, and this works as an optomechanical switch. And what you can do now is attach this device to the Casimir latching device, this thing there. And once you do this and you do your switching, you can turn off the voltage. And it will stay there without using any energy. And then you can turn on the voltage again and reverse, put it down, turn off the voltage, it will stay there again. So what this device does is that it enables other stuff to stay there without using any energy. And that's it. If you want to know more, come to the poster.
Thanks. Thank you.
My name is Benjamin Strzecka. I'm a student of Alejandro Rodriguez at Princeton. So I made a poster sharing some details of our that we recently did. So maybe some background story is actually more useful than all the equations. So Rodriguez was working on calculating bounds on electromagnetic problems. So I guess one example would be, suppose you want to structure some sort of object that had to fit in a ball. One question is, what's the maximum power that you can emit in the far field? And so obviously, for big objects, there's the Stefan-Boltzmann law, so you know that you have to scale as the area. But then the formulas that they developed, they worked for all length scales. And so one of the primary problems for me to work on in the group was to consider non-equilibrium Casimir torque. So actually, Matthias Kruger, actually, when he was a grad student at MIT working for Carter, they actually found trace expressions in terms of the scattering operators for heat radiation and forces. But in none of their work did they consider torque. So I ended up finding that, so if you start from the force expression, which is the Lorentz law, the second line is what Muller and Kruger derived in that paper. And one would naively think, well, torque is just R. So you pick the origin to be at the center of mass of your object, and you do this integral. You would think that the torque on the body is just the same thing, but with this factor of R, right? So you get a orbital angular momentum operator. But actually, it turns out that if you do that, you get the wrong answer. And one question is, why is that? And actually, it turns out that the correct way to do it is you end up what's called the J operator, which is L plus S. So that was like one. neat discovery in the work is that it turns out, for some reason, Kruger, in any of his papers, hold up, sorry. They never considered torque expressions, but if you do it, yeah, you get the J operator, and so we know why. And the other part is then, like, knowing the correct expression for the torque on a body, you can then calculate bounds on the torque. And one interesting thing that's different from power expressions is actually, if this was a power thing, then once you increase the radius divided by the lambda, eventually it would become flat. You get the black body limit, and here you get volume scaling both in the small object limit and then in the far field. And then obviously the formula also generalizes to multiple objects, but yeah, if you want to learn the details, then come to the poster.
Okay, thanks, Benjamin. Now, yes, Ignacio, please. I think you have fresh and.
Hello. Hello, everyone. So my poster is about the longitudinal components and screening of the Casimir interaction between spheres. We are interested in how the zero frequency Matsubara is screened by the presence of ions. So my poster is divided in 5 sections, and the first is an overview how the first one in the second one is an overview how this problem is interesting. The third and the fourth, we developed the work, so we approach how the Casimir interaction appears in the scattering approach, and we see that the scattering matrix is different and they have a longitudinal and TM coupling that does not appear normally. And the final remarks is just that we have still working on this problem. So come to my poster to have a conversation and have more ideas to work on this project.
Thank you, Larissa. So the next one is it's here. Beverungen, please.
Thank you. Yeah, hi everyone. Is it on? Yes. Okay. My name is Bettina. I'm currently a PhD student at Humboldt University Berlin, working with Francesco Intravaglia in the group Theoretical Optics and Photonics of Professor Kurt Busch. And on the poster, I am presenting a smaller part of a larger project that was mainly initiated by Philip Christensen, who is currently at the Technical University of Denmark. And it's about a numerical framework to calculate quantum fluctuation-induced interactions, like the Casimir and Casimir-Polder interactions. And there has been, of course, some previous work on this, most notably from Stephen Johnson and collaborators, who used finite difference time domain methods and also boundary element methods to calculate these interactions. And the main insight was basically that since in the Casimir and the Casimir-Polder interaction, we need the electromagnetic green tensor in order to describe the behavior of the macroscopic objects, we can actually use standard numerical electromagnetic software to calculate this, because the green tensor is directly related to the response of the system to an oscillating dipole. And so here we revisit this time domain method or formulation, but we modify it to use it with a so-called discontinuous Galerkin time domain method, which basically combines a finite element-like spatial discretization, which you can see there on the right, with an explicit time stepping method. And this has several advantages. For example, you can use those sort of unstructured meshes, which are better suitable for complex geometries. And you also have a better convergence behavior than in finite difference methods, which makes it more suitable for high accuracy calculations. Yeah, and on my poster, I'm focusing more on the Casimir-Polder interaction. And there we've, just to validate the numerical method, we've compared it to an analytical reference calculation for a planar geometry, where you can independently just analytically calculate the result. And one of the nice things, so here on the right, you can see a calculation of the Casimir-Polder interaction energy for a rubidium atom above a gold half space. And the numerics and the analytics fit pretty well. And one of the nice things is you can actually reuse the same numerical green tensor calculation, which is the most expensive part about it, and then use it, for example, for different atom species or different polarizable particles, because the polarizability is only accounted for in a post-processing step. And yeah, one of the other nice things is that we can then immediately use all, for example, advanced material methods that are already there in the implementation. And on the poster, I also show that we can reproduce the analytical results not only for a local model, like here we've used the local Drude model, but also for a non-local material description like the hydrodynamic Drude model. Yeah, and if you want to know more, please come to my poster.
Thank you, Bettina. So the next one is Sprang, please.
Hello, everyone. I'm Benjamin Sprang. I'm a postdoc at UC Davis with Jeremy Monday. And yesterday, Jeremy showed us some experimental results in those geometries, which are like between a structured surface and a sphere. And the experimental results were compared to some approximations, like the proximity force approximation. And what I'm trying to do, and that's ongoing work, is to do an exact calculation of the force in those geometries. And in general, it's a pretty challenging task. And what I'm proposing to do in my poster is to use the scattering formalism to calculate that. And yeah, so I would appreciate any suggestion or ideas to for doing an exact calculation of those geometries. Thank you.
Thank you, Benjamin. Next is Tsuri Kami, please.
Hello, my name is Yoichiro Tsurimaki. I'm a postdoc from Professor Shanfui Fan's group at Stanford. So there has been emerging interest in thinking about the radiative heat engine operated by radiative heat and a momentum transfer in non-reciprocal systems. So in this work, we consider radiative heat and momentum transfer between two slabs where one slab is moving with respect to the other. And we point out that under right conditions, the non-reciprocal surface wave supported by these two slabs can enable the radiative heat flux from a lower proper temperature slab to a higher proper temperature slab as the velocity increases, and therefore operating the system as a photonic heat pump. We also discussed some dynamic efficiency when the slab is moving at the relativistic speed. And the efficiency expressed by this way, we prove that it's bounded by the current efficiency. Finally, we explore as a potentially interesting system two suspended graphenes where one graphene is under DC bias to assimilate moving media by moving carriers. So yes, I'm happy to discuss. So thank you very much.
Thank you. Thanks. And finally, we have Rubio.
Hello, my name is Rodrigo Lopez from Purdue University. I am a postdoc in the group of Subin Jacob. And yeah, well, basically my poster relates to the work that I am doing now. I am working on photon statistics, a bit differently from what the conference is doing, but we are also suggesting how to use field correlations for measuring, for characterizing binary systems. In particular, we are applying our general theory to the case of binary stars. Why to binary stars? Well, because in principle, binary stars are very common objects in the universe, and they are very useful for characterizing the stars. And in principle, we need to have a good characterization of the stars in order to be able to describe the life of the stars and the evolution of the universe. Okay, so in principle, what we are doing here is an extension of the Hamburg-Brown twist experiment that basically measure photocoincidence into detectors, and we are proving that we can use the same technique that is right now available in the telescopes, also for measuring the temperatures of the stars. Okay, that this was not done before. In principle, we are extending the formalins using the Glauber P functions. Okay, and yeah, and well, basically that is what my poster is going to be related. So if you are curious about how to use the field correlation for this kind of characterizations, I mean, we apply it to stars, but also the same theory can be applied to cold atoms. You can come to my poster. If you want to know what is the best strategy to use for such systems, you can also come to my poster, okay? But if you are not interested in these things, you can also come to my poster, okay? And we can have a chat, okay? Thank you very much.
Thanks, Adrian, and thanks to the rest. So I just want to remind you that we can have a discussion at 5:30 and also tomorrow at 2 and at 5:30, if I'm correct, but without these fast slides. So shall we move to the, yeah, until to fit to the schedule. Okay, let's stop here then.